Hello everyone, I hope everyone is doing well today. So I'm Anais Nathalie Mkrtchian, and today I'm going to present my capstone project, which is the embedded design of a pulsed-field ablation circuit for cardiac applications. And my supervisor was Anais Nathalie Mkrtchian, who couldn't be here unfortunately today. And my advisors are Tigran Solomonian and Wahab Avaken. So before I dig into the whole capstone project, let's have a presentation overview. So first of all, I'll introduce what a PFA device is, why we use it, then its clinical significance and market. Then I will start talking about the system design, my part of the project, and then the implementation and results, and finally the limitations, conclusions, and future work. So first of all, we need to understand what ablation is before we understand what PFA is. So ablation is basically a medical procedure that is used to destroy or isolate abnormal tissues. And since my capstone is about heart, it is related to the heart in cardiology, it is commonly used to treat arrhythmias, which is irregular heart rhythms. So basically, in atrial fibrillation, abnormal electrical signals disturb the normal rhythm of the heart, and the goal of cardiac ablation is basically to target that irregularity and try to reduce or stop that abnormal rhythm. So traditional ablation methods that have been used in the past and the most common ones are radiofrequency and cryoablation. Can someone tell me what's their similarities or something in common that you might notice when I say radiofrequency and cryoablation?
No one knows.
So there.
I was asked the question during the posting.
I mean, if you want, you can answer. So their main similarity is that they both use temperature to get rid of that irregularity. And although in the research that I've made, it showed that usually they've been successful. It also showed in the studies that they tend to harm a perfectly heart or cells that are around that cell membrane that is causing those irregularities. And that's where PFA comes in. So pulse field ablation, or PFA, is used to control electrical pulses to selectively disrupt the cell membrane that is causing the distress or the irregularity of the heart, and it's basically causing cell death via necrosis and apoptosis. And it is one of the it's the most recent method that is now used for ablation, and its key advantage is that it is non-thermal. So it is basically we use it for we transfer electrical and we do electroportation, and basically what that means is that electroportation happens when an electric field creates tiny pores in the cell membrane, and if the pulse is strong enough and the parameters are what we expect and etc. is sufficient, then the membrane cannot recover, and finally the cell eventually dies, as is shown here. So its main advantage is also that it's tissue selective, which is making it safer and more precise for treating cardiac arrhythmias compared to conventional thermal approaches. So why are we working with this new device? Why this new approach? So current PFA generators rely on expensive external function generators, and they lack integrated low-cost microcontroller-based control, which is also why in Armenia, for example, we don't have that device yet in laboratories or hospitals. So our solution was to, with the device that Tigran and Vaha created, we wanted to replace the benchtop equipment with the compact STM32 based controller. And why did we use STM32? Because it's reducing the cost, and also what I studied during those 4 years at the university. So the clinical requirements is that it is programmable, so we can control the parameters and how we want to conduct the device. It's cost effective and it's more precise. So its clinical significance and market. So we need to understand why PFA is important before getting to the embedded part. So the limitations of current ablation technologies is that, as I mentioned, radio frequency and cryoablation, they use heat and they can cause pretty dangerous damages to the heart. And as shown in the pictures, it is mainly damaging the esophagus and damage the phrenic nerve, while the pulse field ablation, as we can see, doesn't do that. So that was also one of the main goals why we chose PFA. And also PFA is now the fastest growing segment compared to those other methods. Yeah, that's why I just wanted to mention this little part and show why it is so important. Um, so now the system architecture design. So my main task was to work on the STM32 peripherals, generating pulse width modulation, pulses, and also working on the timers and etc. So I had to understand how the hardware first of all and what the device is before doing that. So the system architecture of the system is basically the user input. So the user input is basically the display that shows all the parameters that we want to control. Then comes the microcontroller core, so the brain of the system, which generates the pulse width modulations. And in the end, we should get square signals, which I'll show after that with the oscilloscope. And so this is basically the main idea of the chain, and the STM32 microcontroller core uses low voltage, while the signal output uses high voltage. This is the hardware device. On top of the low voltage is actually the display, and this is the main area where I worked on, because the high voltage, the other part area of the device were already developed. We just didn't have a system, and that was the main issue of the device. So the user input display. So here we have, this is the main idea of what you would generally see in a PFA device. So what we have is the pulse period, which controls the time duration of one complete pulse cycle. Then we have the pulse duty in a percentage, the count of pulses, so the amount of pulses that we want to generate in one sequence, the frame interval, so that's all, the delay, the process length, so how long we want that simulation to happen, and the combination. So the combination is actually put for future work, which I'll mention later, but right now this is just random numbers displayed. But number 4 means that on the device, the number 4 channel is the one that we use for to do that experimentation. And then we have the voltage set point, so how much voltage we use to do that experimentation. So the PWM generation that I used with STM32, I mostly worked on hardware timers, because they generate pulse waveforms, and pulse width modulation is started through Hall timer function. So in my project, for pulse width modulation was generated using STM32, and the main idea of this is to get that frequency that we wanted. And when we compare why did I use pulse width modulation instead of delays? Well, the main problem was that when we use delays, we have to manually control it, while as for pulse width modulation, it does the job automatically. So that was why I worked on pulse width modulation. And this is just a little part of the code to show the main function that generates that pulse width modulation. And then we also had the GPIO and output enable control. So the GPIO is basically the input and output that we want to control, and etc. The pins for switching and enabling the signals. And in the firmware, the GPIO pins can be set high or low using call functions, and this allows the system to activate or deactivate parts of the circuit during testing. So implementations and results. So this is gonna be interesting. It might be weird, but I'll show you. So this is the electrode that we used. Its distance, so those little sticks that we see, its distance is 1 centimeter. When I was doing the research, usually more professional electrodes, or called catheters, they are usually from 4 millimeters to 6 millimeters. But why we chose specifically 1 centimeter is because we wanted to experience first on we wanted to experiment first on potatoes before we actually work on cells or tissues. And the reason why we chose potatoes is actually because potatoes are very similar to hard tissues when it comes to electroportation. And that was very surprising for me actually. But yeah, so, and it's very accessible. So we wanted to try and see if the device actually works with the program that was created to then actually work on the tissues that we want. So what we had first was, after 1 minute, we don't see anything obviously, but after a day we have dark spots and burns, which means that the signal was generated and it worked. But I want to make it clear that this was just an experiment to see if the signal is actually, if the output was given or not, because and it's not an electroportation to kill the cells. This was just an experimentation to understand if the system that was made work or not. The same parameters that we use for the potato, we also measured it with an oscilloscope. And when we measured it, we used almost 1,000 voltage, and the waveform showed that it was rectangular pulses. So that's actually good, because we need constant pulses to damage the cell that causes those irregularities. We need that consistency. So for example, if instead of a rectangular signal, it was some non-constant or abnormal pulse, then we wouldn't have the guarantee that the cell would be dead. The cell that we want to kill wouldn't be dead. And so the cursor measurement indicated here is that in 41 microseconds, corresponding to a repetition frequency of approximately 24.39 kilohertz. And yeah, so that confirms that the device generated a controlled pulse that we wanted. And again, after this confirmation, we know that now we can use the parameters that we want to actually kill the cells, to experiment on the cells that we want. We also compared the PCB signal output and electrode signal output to understand if the output that we get from the electrode is the same as the PCB. And as we can see, is that both of them are almost identical. It's just there's a little bit of noise for the electrode signal output, and that could be due to the connection, for example, how we connected that electrode to the PCB. And yeah, it validates that pulses reach to the external output path. And so for conclusion and future work, so the limitations right now that we have is that it's a prototype level system. It's not clinically labeled yet, I'll say. And so as I said, we tested on potatoes. So the next step would be cardiomyocytes or cardiac tissues. And then we don't have proof yet that it's electroportation. The only proof that we have is that the signal was generated. And we need to also enhance the device, the system overall, because right now we have DC and we also have another AC system. So we need to also work with that to make sure that the system works for both circuits. The conclusion, though, is that we successfully developed a microcontroller-based pulse generation system for PFA. We were capable to produce accurate, stable signals, as I showed earlier with the oscilloscope, and that the results demonstrate that the system's reliability and effectiveness for future biomedical applications. And for future directions, I would say that first of all, we need to do more experiments on the cardiac tissues and the cardiomyocytes. And when those protocols are accepted, then we can change the microcontroller to something that is more advanced, that can give more channel output. So for example, I want my device to have 4 outputs to generate different frequencies and different pulses. So yeah, that's the main idea for the future work. And acknowledgement, I would like to thank Dr. Anais Nathalie for her guidance, encouragement, and valuable feedback throughout this journey. Also, the Orbeli Institute of Physiology for providing the supportive research environment, and also for giving the tools that I need and connecting the engineering work to biomedical applications. Tigran Solomonyan and Vaha Gavakian for their technical support, also emotional support, advice and collaboration during the design, development, and testing stages. Mariam Mkrtchian for her constant support and amazing guidance during this process. And finally, my friends and family for their patience, motivation, and encouragement throughout this project. And I want to congratulate all my peers that presented today and are going to present. We did this, guys. Thank you.
Good presentation. Great. And you showed the big device, and that we have
Yeah.
small piston there. What is big device before you use it? What's that for?
I'm sorry, can you ask again the question?
What it is for?
The big device.
Yeah. It is
So
big.
that's the yes. So we're trying to create our own PFA device, and when I was introduced to that device, it was only DC. It was a DC circuit, and that device we want to create to then use it for laboratory works at the Orbeli Physiology Institute. And so my task or my goal was to make a program that can be usable enough for the beginning, and then from that point to extend and just improve. Thank you for the question.
You talked about the darkness or the spots on the potato being only sort of proof of qualitative and not
Yeah.
quantitative, and maybe no, you can suppose, but maybe you can't prove that it's
Yeah,
electroportation.
electroportation, yes.
Okay. I'm just curious, what additional, I don't know, either sensor or comparative, burn it with a match and compare. I mean, what else might you have been able to do to actually
To
get
for
some
the potato
quantitative-
specifically.
Yeah, to get some actually quantitative substantiation for what you are showing is qualitatively demonstrated.
So that's a really good question. Thank you. So I would say that we have also, when we did an experiment, I would say that we could cut that specific area, and we have special stains that we can look under special microscopes. So I would say that we could do also that step and see what we have, if we have any cells or if we don't have. So we basically, what we can do is we can compare a healthy potato that it has not been affected by the device and the potato that was experimented and burned per se, and then we can see if the differences of the cells, the amount of cells, and etc. And then maybe I think from that we can also make a conclusion about that electroportation that you asked for.
Okay, so maybe that's like a future work.
Yes,
that someone
definitely
could do
future
in
work,
terms
yes.
of quantitative or calibration. Of
Yes,
some
because
sort.
before we do experimentations on cardiomyocytes or cardiac tissues and etc., we need to make sure that the protocol meets every requirement and that the protocol is accepted. Without the protocol, we can do any experiments.
We'll be happy to sacrifice another potato or two before we
Yes.
offer someone's heart for your experimentation. Yes.
Yes.
The quality.
Yes. Paula's budget is a percent.
Is there any other questions?
Thank you.
Thank you so much.